So what we are looking at here is this coil. Yeah, imagine my phone is the coil. So this is the coil. The outer edge of the phone is the coil. All right. So there is certain magnetic field. Imagine this stylus is the magnetic field. This phone is right on the plane of the magnetic field. That means the phone is not like this or like this or like this. At one instant, the phone is along the direction of the magnetic field. Maybe later in time, it's going to rotate, but we don't care about that. First, you imagine the phone is in the direction of the magnetic field. The B field is along the x-axis. So the B field is going to have certain Bx in the x-hat direction. You don't know what is Bx, but it's positive, but it's in the x-hat direction. So it's B naught x. So if I have this loop of current in that plane, in the plane of the B field, which plane is in the B field? The B field is in the plane of, let's say, XY plane, which means my Z is coming out. My Z is coming out. Z is coming out. X cross Y, Z is coming out. So I have 4 sections here. I have section 1, 2, 3, and 4. And the direction of current is this way. It's making a counterclockwise direction. Having said this, I can break up this problem into 4 sections and do the direction of the current, orient the fingers in the direction of current, and curl to the direction of B. The thumb gives the direction of the force. So if I were to do that for, let's say, this section, the current is going down, the B field is to the x-axis. When I do that, you see that the I cross B is going to be coming out of the slide, which is exactly in the z-hat direction. So this guy, the force, or maybe I use the red color. Use the red color. So that is going to be my force. What is the difference for B? For B, it is only difference is the direction of the current is opposite to section 1. For section 3, the direction of the current is opposite to section 1. So this case, the force is going to be acting inwards. If you're not convinced, hold your right hand, fingers along the direction of the current, and do the cross product with respect to B. So your thumb is going into the slide. But how about this guy, or let's say this guy too, right? The direction of the current is parallel to B, right? The direction of the current is parallel to B. So your IL cross B for this guy is going to be equal to 0 because two opposite vectors, I and B, the angle between them is 180 degree. They're opposite to each other. So 180 degrees, sine 180 is 0. How about this case? This cross B is going to be 0 as well. So if I were to view this guy from, let's say my eyes are over here, if I were to view this guy from here, yeah, and if I were to view like this, then all that I see is the x-axis is here, the z-axis is here, and the y-axis is going in. The y-axis is going in. I see that this vector is this guy here, the f1, and this fz, f3 is going to be this vector here that is going down. So this is my f3. There is no force here and there is no force here on those 2 sections. So clearly you can see that you are applying F1 at a distance D1 from the axis of rotation in the clockwise direction. And this guy is going to be negative z-hat direction at D3. So this is in the clockwise direction as well. Then this means the whole thing is going to rotate in the clockwise direction. If this entire length is A, this distance where that force is going to appear is going to be A upon 2. So how do I go about doing it? Now I want to find this IL cross B, that you don't have to do I integral DL cross B. You don't have to do this. So, I mean, technically that is what you are doing, but all these line segments are going to be individual lines like this, 1, 2, 3, 4. So if I break it up, F1 is going to be my current in the direction of negative by hat. Because the current is going down, it's opposite to y. So this is going to be I negative b, yeah, b being the length of the vector, b being the length of the vector in the y hat direction. So this is my IL hat, IL vector for section 1. Cross b, b is b naught x hat. So if I do that mathematically, I get IB b naught z hat. You got your F1 in the z hat direction. Mathematically, you'll be right. If you're not convinced, use your right hand, or you do mathematically, you'll be right, because your y cross x is negative z. Y cross x is negative z, and the negative becomes positive. The same with F2, you see that x cross x is going to be 0. The same as F4, x cross x is going to be equal to 0. For F3, you left with y cross x, which becomes negative IB naught z. So you got 1, 2, 3, 4. Of the 4 forces, only 2 of them contribute to torque. The other 2 are already 0. They don't actually contribute to the torque, and they are also 0. It is only F1 and F3 that matter. How do I find the torque now? I need to do the D1 cross F1 for force 1, and I need to do D3 cross F3 for force 3. So I got to do D1 cross F1 for force 1. The small letter a is the length of this section. It's a rectangular coil. It's a rectangular coil. This length is A and this length is B. So L captures the length law. This guy is the length in the L hat direction, yeah, whether it is X or Y or Z. Then you have this D3 cross A. So important thing for you to notice, your D1 is in the negative X hat direction, because the point where that force applies is going to be minus A by 2 X hat. That's going to be D1. It's minus A by 2 X hat because it's in the negative X hat direction. It's your D3, which is going to be plus A by 2 X hat. So when you go ahead and add it up, you get IAB B naught. IAB B naught in the Y hat direction. What do you observe? A times B is the area of this guy. So you have the area of the loop, which is A. A times B is the capital A. B naught being the magnetic flux, I being the current, and Y hat is the direction of torque. What do you mean by direction of torque? If you have an object that is rotating, orient the fingers of your right hand in the direction of rotation. Your thumb gives the direction of torque. If you have an object that is rotating, take your right hand and curl the fingers along the direction of rotation. Then the thumb gives the direction of torque. So in this case, you know that this guy is going to rotate in the clockwise direction, right? In the clockwise direction. Take your right hand, rotate all the fingers in the direction of the rotation, which is clockwise in this case. Then the thumb gives the direction of torque, which is going in, which is the same as the Y hat. So that's why your torque is in the Y hat direction. Yeah. So torque is a vector because it's a cross product of position vector times the force. So the direction of the torque represents, in a way, the direction of motion, movement, rotational movement. If your right hand fingers are all curled in the direction of rotation, the thumb gives the direction of torque.